We're continuing our discussion of the rotating charged rigid bar. And remember that this bar is in a uniform electric field pointing in the plus j hat direction. And we have found the potential as a function of y and the potential energy as a function of angle theta and the initial potential at y is equal to 0. And we have found the value of V0 for the potential energy to vanish at theta is equal to 0. And then we have released the bar from rest at the position 90 degrees and found the angular speed at theta is equal to 0 degrees using conservation of energy. Now part E says if the bar starts from rest at a small value of theta. So we have a small value of theta around 0. With what frequency will the bar oscillate around the position theta is equal to 0 degrees? Okay, so remember that we have this potential energy expression here we have obtained in part B. Now we are very close to the angle theta is equal to 0. So let's find how this potential energy behaves in the vicinity of theta is equal to 0 degrees. Okay, so let's look at the Taylor series expansion of cosine theta around theta is equal to 0 degrees. So first thing we do, we evaluate cosine theta at theta is equal to 0 degrees. Then we take its derivative, which is minus sine theta, evaluated at theta is equal to 0 degrees, and then theta minus 0, and then we take another derivative, minus cosine theta divided by 2 factorial, and evaluated at theta is equal to 0 degrees, theta minus 0 square, etc. So this is the Taylor series expansion. Now you can see that cosine 0 is 1, sine 0 is 0, so this term will disappear, and cosine 0 is 1 again. So I will obtain basically theta squared over 2 for the last term. Okay, so this is going to become cosine 0, which is 1, minus theta squared over 2. The first two non-zero terms. So the potential energy around theta is equal to 0 degrees is going to be Q. So I'm copying this result here, Q times V0 minus E over 2L cosine theta, Q times V0 minus EL over 2, and for cosine theta, I'm going to write 1 minus theta squared over 2. So this is going to give me Q times V0 minus EL over 2, and then I have plus EL theta squared divided by 4. That's the potential energy around theta is equal to 0. Now the kinetic energy as this bar oscillates will be due to its rotation. So it's 1/2 I omega square, which is 1/2 I the derivative of angle with respect to time, theta dot square. And throughout the motion, kinetic energy plus potential energy is a constant. Therefore, if I take the time derivative of the mechanical energy, I will find 0. K dot plus U dot is 0. So what is the time derivative of kinetic energy? It is 1 over 2 2I theta dot, first time derivative, theta double dot, second time derivative. This must be equal to minus u dot, which is minus, now you can see the time derivative, it will not affect this term or this term, these are constants. It will affect this term because it contains theta in it. So I will obtain minus QEL over 4 2 theta dot. Time derivative of theta square is 2 theta dot. So this will get rid of this 4 and make it 2. And I will obtain, also these 2's will disappear. I, moment of inertia, theta dot, theta double dot, second time derivative, is equal to minus QEL over 2 theta dot multiplied with theta. Now you can see that I have two angular speeds here, theta dot, theta dot. They will cancel out. And I will be left with this equation of motion. Theta double dot is equal to minus QEL over 2I theta. So let's write the equation of motion. Theta double dot, second derivative with respect to time, is minus QEL over 2I theta. Now, moment of inertia I have found in part D to be ml squared over 3, so I can substitute that. So this will give me minus QEL over 2 ml squared over 3. That's the moment of inertia for oscillations around the end point. I see that one of the L's will disappear, and I will obtain theta double dot is equal to, this 3 will go upstairs, minus 3QE divided by 2ml theta. Now you can see that this is in the form of x double dot is equal to minus omega square x, the differential equation that describes simple harmonic motion. This is the equation of motion, EOM. So the corresponding angular frequency, omega, is 2 pi times the frequency. It is the square root of 3QE over 2ml. So that means the frequency of the oscillations will be 1 over 2 pi times omega, which is 3QE over 2ml square root. So this is our final answer. So this is one way to solve this problem using the energy approach. Alternatively, we can think about the torque. So alternatively, one can write the torque equation. The net torque acting on the rigid bar is moment of inertia times the angular acceleration. So if you concentrate on this bar, if you look at any differential element of the bar here, it's going to feel a force dF because it's positively charged. It's in the direction of the electric field. EQ is going to be E times dQ, will be pointing in J hat direction. This will have a component that will go through the pivot point, and it will have another component which is perpendicular to the bar, which is dF perpendicular. So the torque that is going to appear on this element, the torque is going to be the perpendicular distance r times df perpendicular. So r is the distance between the location of the infinitesimal element and the pivot point. Now you can see that the perpendicular component of this force, because this angle is theta, this angle is theta, will be df sine theta. So it is going to be r df sine theta. And what is df? It is the electric field E multiplied by dq, which is E times lambda dr. The torque is, by definition, r cross f. The net torque will be the integral d tau, which is the integral from r equals 0 to r is equal to L. R, the perpendicular distance, for df sine theta, I'm going to write E lambda sine theta dr. So this is going to give us E lambda sine theta L squared over 2. Because integral of r dr is r squared over 2. Evaluate between 0 and L, it is L squared over 2. So I will find that the torque is E times lambda, which is Q divided by L, uniform charge distribution, sine theta L squared over 2. One of the L's will disappear, and I will find that this is EQ sine theta. For sine theta, I can substitute approximately theta, because theta is close to 0 degrees. So this is going to be EQ theta L over 2, and this must be equal to I times angular acceleration. Now, is this torque going to increase the angle or decrease the angle? You can see that it acts to decrease the angle. So this is basically trying to come closer to the y-axis. So therefore, this is minus I alpha, which is minus I theta double dot. And the minus sign basically is due to the fact that since torque acts to decrease the angle theta, not increase, therefore it's going to have a minus sign. So we obtain the same equation of motion. You can see here, this is the same equation of motion. Therefore, we have the same solution. So we could choose to follow the torque approach or the energy conservation approach. Okay, so in this part of the problem, we have the bar starting from rest at a small value of theta. It will oscillate around the position theta is equal to 0 degrees. So what will happen is it will oscillate back and forth around theta is equal to 0 degrees. And the frequency of that oscillation is what we are after. So we followed the energy approach. First, we write the potential energy for small values of theta using the Taylor series expansion of cosine theta around theta is equal to 0 degrees. And then we write the kinetic energy, which is rotational kinetic energy, 1/2 I omega square. And then we note that the mechanical energy does not change in time. We have conservation of energy because there are no dissipative forces. Therefore, k dot is equal to minus u dot, the time derivatives. So we will find the equation of motion, which is in the form of simple harmonic motion. From this equation, we read omega, which is equal to 2 pi times the frequency. Alternatively, we write the torque R cross F for each charge element on this bar, we see that this force has a perpendicular component, which is df sine theta. And for the force, we write E times dq, where dq is lambda times dr, where lambda is Q over capital L for uniform charge distribution. We integrated from 0 to capital L for R values between 0 to capital L to find the total torque, because they each have the same, each charge element has the same orientation of the torque, the direction of the torque, so they add up, and therefore we obtain the equation of motion by noting sine theta is approximately equal to theta for small values of theta. We have the same equation of motion that we have obtained using the energy approach. So the negative value of this alpha minus I theta double dot comes from the fact that the torque acts to decrease the angle rather than to increase it. So we obtain the minus sign required by the equation of motion form of the equation of motion for simple harmonic motion.